Okay, so now let's move on to the triple product. Let us now add a third vector to define a three-dimensional structure called a parallelepiped, with sides given by the vectors A, B, and C. Now the volume of this parallelepiped is equal to the area of the base multiplied by the perpendicular height. Now the base is simply the original parallelogram that we had before. So the area of the base is going to be equal to the magnitude of the vector A cross B. And then H is given by the length of C multiplied by the cosine of the angle between the vector C and the vector A cross B. And therefore the volume will be given by the magnitude of A cross B multiplied by the magnitude of C multiplied by the cosine of the angle between them. And you can recognise that as simply the dot product between A cross B and C. This combination is called the scalar triple product. Now it's important to make sure that you do the cross product before the dot product. The other way around doesn't make any sense, because if you do the dot product first, you only have one vector left. Note also that this triple product can be negative, so in which case the volume is really the absolute value of the triple product of the vectors A, B, and C. Now let's do an example and find the triple product of the vectors A, 2, 4, minus 3, B, minus 1, 0, 3, and C equal to 2, 5, 4. Now we've already worked out A cross B. And that was given by 12 minus 3, 4. So to form the triple product, we simply multiply this by C, so that A cross B dot C is going to be 12 minus 3, 4, dotted with 2, 5, 4. And so the volume is going to be given by 24 minus 15 plus 16. In other words, it's equal to 25 units. Now there are a number of symmetries of the triple product. The first few come from the symmetry and anti-symmetry of the dot and cross product. So A cross B dot C is equal to C dotted with A cross B, because the dot product commutes. However, if I swap A and B round, then because of the anti-commutivity of the cross product, this gives me minus B cross A dotted with C. Finally, there's a symmetry that comes from the parallelepiped itself. Originally, I took the base to be A cross B. However, I could equally well take the base to be B cross C, and so we have that A cross B dot C is the same as A dotted with B cross C. Now to check this last identity, we can calculate A dot B cross C and show that it's equal to 25 as we found before. So using my first method, B cross C is going to be given by minus 1, 0, 3, and then repeating the minus 1 again, and 2, 5, 4, and repeating the 2 again. And then doing my usual diagonal lines, I get first of all minus 5 in the k direction, 0 in the x direction, and then 6 in the j direction. And then doing the opposite diagonals, I get minus 15 from 3 times 5, minus minus 4, which gives me plus 4, and then finally 0. So B cross C is equal to minus 15, 10, and minus 5. Therefore, A dot B cross C is equal to 2, 4, minus 3, dotted with minus 15, 10, and minus 5, which gives me minus 30 plus 40 plus 15, which is 25 again, as we found before. Combining together all these symmetries, we have A cross B dot C is equal to A dot B cross C. So we can swap the dot and the cross around, which is equal to B cross C dot A, using the symmetry of the dot product. And now swapping the dot and the cross again, I can get B dot C cross A, and once again I can swap that round as C cross A dot B. And so what you can see is that the triple product gives you the same result for different orders of A, B and C as long as they are cyclic permutations. On the other hand, if you swap any two of the letters, for example, if I swap the B and the A, I get minus B cross A dot C. Now we can see all these properties when we use the determinant form for working out the cross product. So remember that B cross C is written as in a determinant as ijk times B1, B2, B3, C1, C2, C3. And therefore, if I dot it with A, I can do that by replacing the first row with A. So I get A1, A2, A3. And now, from the properties of the determinant, we know that we can swap round the rows in a cyclic manner and the determinant stays the same. Also, if you swap any two rows, then you change the sign of the determinant. What this also means is that this gives you a way of interpreting what you mean by the determinant of a 3 by 3 matrix. It's essentially the volume generated by the three vectors that correspond to the rows of the matrix. And finally, if the determinant is 0, what that tells you is that the volume of the parallelepiped is 0, which means that all three vectors lie in the same plane. So working out the triple product, and if it's 0, that gives you a way of determining whether all three vectors are coplanar. Thank you.